Okay, we are going to continue talking about derivatives today. This particular lesson is progressive. I'm going to go ahead and give you a few more problems where we ended off yesterday, where we're just finding what's called the gradient of the secant line. So you'll notice when you're given that particular wording, we're leaving it in terms of h. When we're asked to find the derivative, or we have a name for it coming up in just a moment, that's when you take the limit. And even at the end of the lesson today, we'll actually be finding the slope at a particular value because we'll take the derivative and then we'll go ahead and evaluate it. But this is the end of the 6 weeks, so Monday is, of course, the start of the final grading period. So we have 5 weeks until what? Until the paper exams. There we go. So I know everybody is probably thinking about that more than anything else. Obviously, okay. So you'll notice with only 5 weeks out, I'm hoping, and we're moving along pretty well, that pretty much by the end of next week, we should be almost completely done with differential calculus. May take us a few extra days into the second week of the 6 weeks, but I've already provided you with the first review. So hopefully, when you have some time, go ahead and start looking this over. You'll notice the first problem, I believe, is sequences and series. Okay. Type of problem. Then you have a scatter plot. Then you have a compound interest problem with currency right after that. So it's going to start covering all the topics that we've looked at through the entire year. In fact, speaking of, has anybody had the opportunity yet to go back and look at any problems on the release test? Mark scheme, anything like that? Okay. Well, I know tomorrow night would be a good time. I mean, who wants to watch Tech win the game? Let's do some math, right? Very cool. Okay. All right, but let's go ahead and continue going. So eventually, we're going to go ahead and talk about these together. I would like to give you the opportunity to try and work these problems yourself before we do that, because it's very likely you'll come across problems very similar to these over the same topics and when you take the paper exam. So we want to make sure we remember how to do that, the calculator strategies, all that good stuff. And I will be posting the answers soon, just not yet. Okay, again, I want to give you the opportunity. Okay, so yesterday we were talking about what we're referring to as the difference quotient. Basically, this formula right here, where f of a plus h minus f of a is over h. And h, of course, represents the horizontal distance between two values of x on a function. We're referring to that as a secant line because we had 2 points of intersection. So we had 2 problems that we were able to do. Let me go ahead and just give you another one real quick. We'll come back and do this one B in just a second. I wanted to go ahead and do some that were very similar to each other before I did one different. So let's say I were to give you f of x is equal to, let's start with a linear function. Let's say 2x plus 5. Okay. And using the same set of instructions we have for the others. Okay, find the gradient of the secant line connecting 2 points for this function. So basically, I want to take this and apply it to the difference quotient. Now, here we have the variable a, but the variable itself doesn't matter. The one that's going to remain consistent is the h. So you could also see it like this. F of x plus h minus f of x all divided by h. And typically, that's how I prefer to go ahead and write it as well. I just kept consistent with what the resource was telling me. Okay, so the way we were doing this, first, let's go ahead and figure out f of x. But what do we notice? We want to apply the formula to this, and part of it is f of x. But we have f of x. We already know what that is. So I know that this portion is just going to be replaced right here. Okay. But now I want f of x plus h. Okay. And just like yesterday, remember we were doing f of a plus h. The variable does not matter. So what is this actually telling me to do for my function? There you go. For every variable I've got, I'm just going to replace it with x plus h. So 2x becomes 2 times x plus h, and then we have plus 5. Okay. And then we can go ahead and simplify this a little bit. What do I get if I double x plus h? 2x plus 2h plus 5. Okay, and there's no like terms, so that's as far as I can go. All right, so I'm going to start the formula by taking this expression. Remember, that is f of x plus h, and I'm going to plug it into that formula. So the first part of the numerator is going to be 2x plus 2h plus 5 minus, then we're going to subtract f of x, but we were already provided f of x when the problem started. The only thing is, what did I suggest you do yesterday?
Keep the f of x in parentheses.
There you go. Keep it in parentheses because you have to distribute that negative. So 2x plus 5, and then this is all over h. So depending on the function that you're going to be plugging into, I mean, you could conceivably have a really large numerator, but your denominator is always just going to be h. Okay. So let me go ahead and remove this down here so I have a little more space to continue. So if I distribute the negative, 2x plus 2h plus 5 minus 2x minus 5 all over h. And do we notice anything in the numerator? Okay. Typically, at least, you know, one pair of terms should cancel. You'll probably have more. So the 2x's are out. The 5's are out. So this one was actually pretty nice to me. When the h's cancel, that one's just 2. Now remember, everything is based on patterns. This is the formulaic way, the basic, the universal method of finding a derivative. As we go through these, you're probably going to start to notice patterns. And that's what the next lesson is about. It's the shortcut, where we don't have to use the formula. We're going to use those patterns that we see. Okay, well now let's go back to B, unless anybody just wants me to make up another one. No? We feel good? Okay. Then B, it says find the gradient, okay, the slope of the secant line joining these 2 points. Now, it doesn't give me a function, but I have to go straight from these points. Now, remember, the difference quotient is based on slope. So I'm going to go ahead and take the difference of the y's and then the difference of the x's. So I'm going to start with 1 plus h squared. Okay. Subtract the y value of the other one, 1. And then I'm going to go ahead and take the difference of the x's, but I'm going to go 1 plus h minus 1. So is everybody okay with how I filled that out? Okay. I started with this one right here. Pretend this is x1, y1, x2, y2. And I just applied our slope formula. Now, the denominator is going to be real easy to take care of. The 1's are going to cancel. They're out there. But I need to go ahead and expand 1 plus h squared. Can anybody tell me what that would be?
2 plus 2h plus h squared.
Very close.
1 plus 2.
There we go. So this would be 1 plus, whoops, I wrote it down myself, 2h plus h squared minus 1. And remember yesterday we talked about some different strategies you could use. You could expand it and use FOIL, the distributive property. Does anybody remember the rhyme I brought up? Square the left, square the right, double the middle. We got it right. And I've always thought it was kind of a sloppy rhyme because all you're doing is rhyming right with right. So maybe we could come up with something that's a little, you know, better fitting for us. Okay, square the left, square the right, you double the middle. It's upside. Okay.
The answer is in sight.
The answer is in sight. Oh, I like that. There we go. The answer is in sight. And in fact, the answer is in sight because we're almost done. So those ones are going to cancel. Now, would anybody like me to go ahead and separate those fractions so that I can show how we simplify the h's, or you would? Okay, then I'll go ahead and do that. Now, these two numerators have the denominator in common. So if you're able to see how it's going to simplify, that's fantastic. But if you want to go ahead and break them apart, what would be my final answer? 2 plus h. Here we go. Because remember, a lot of the rules that we use in mathematics are reversible. In order to add or subtract fractions, you need a common denominator, but you can break it apart as long as there is that common denominator. Okay, so how do we feel about using the formula? Are we ready for the next step? Okay. So this has just been using the formula. Now, whatever answer we get, the next step will be to take the limit as h approaches 0. And this is what the next section is talking about. Okay. When we look at the instantaneous rate of change at one point on a curve, say xy, it requires that we use a limiting process to observe the average rate of change between another arbitrary point where we have a distance created from it using h. As q becomes closer and closer to p, that is, as h gets closer and closer to 0. Okay, so all we're doing now, we're still taking the formula, we're applying the function to it, but here is the new portion. We're going to take the limit as h goes to 0. Okay. So the rate of change, okay, of f at point p x f of x, we call that the gradient function, or by taking the limit, we can refer to that now as the derivative. Okay, and the derivative is very, very, very useful to us. All right, the derivative of a function f is denoted by f prime of x. Okay, and they say dash. I've always said prime because in geometry, that's what I got accustomed to. Do you guys remember when you did say reflections and rotations and things? If you had point A, then you had A prime. But if you want to refer to it as dash, that's, whatever you like. Okay, or F prime. So if I were to have function g, and I wanted its derivative, I could refer to it as g prime of x. Okay. There's also another notation that is most likely going to come up. You could say it like this, dy dx. Okay. The change in y divided by the change in x. But this notation is another way of showing the derivative. Okay. All right. And we can also refer to this, finding the derivative of a function using this approach is referred to as finding the derivative of f from first principles. Okay. So let's just get right to it. Let's get to a problem. Using the first principles method, find the derivative or the gradient function of the function. Now you'll notice the directions here are a little different because part of what we're doing next week, I'm going to have a quiz for you. And on the quiz, I've copied the instructions exactly. It'll say find the gradient of the secant line, okay, for a couple of points. Well, what that's telling you to do is apply the formula, but don't take the limit. You're going to leave your answer in terms of h. But if I go ahead and tell you, okay, first principles method or find me the derivative, you will take the limit as h approaches 0 of whatever expression you get. Is everybody okay with that? Okay. Eli, are you raising your hand or are you just?
No, I'm
okay. Okay, just want to make sure. Okay. All right. So we have a here. F of x equals x squared. Okay, so I want to go ahead, take the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. Well, first we need to go ahead and get the two items in the numerator that we need. I need f of x, but just like that example I gave you a moment ago, what do we notice? We already have it. So f of x is x squared. Okay, that's what I'm trying to find the derivative of. Yes, ma'am. Oh, you'll still do it with the formula, no matter which way. But if I just tell you, as it says here, to go ahead and find the gradient of the secant line, that means you're leaving it in terms of h.
Okay,
But this, we will not have an h in our answer. Oh, yes. You'll have to use the formula. Because it very well could be, a problem on the paper exam. They could actually ask you to use the formula in order to find the derivative. Well, do you remember derivatives? Okay. So what should I be getting as a derivative? What's the derivative of x cubed? Very good. Now I'm going to throw a challenge at you. What's the derivative of 1 over x to the 4th? Now, is anybody seeing what she said? The derivative, the answer we should be getting on A is 2x. She said the derivative of x cubed is 3x squared. Anybody think they know what she's doing? This is what the next lesson is about, is using the shortcuts. Okay. She's absolutely right so far. So for A, I should get 2x, and for B, I should get 3x squared. Okay. So I'll tell you what I'll do, I'll go ahead and move this one 1 over x to the 4th. I'll move that over to the side, and we'll see if in a little bit you can remember how to do that. Okay. So now let's see if we actually do end up with 2x on this first one. So we got f of x equals x squared, right? Everybody's good?
Yeah.
But I need to figure out what f of x plus h is. So f of x plus h, well, again, for every x, I'm going to replace it with x plus h. So that's just x plus h squared, which would be what? Okay. So square the left, square the right, double the middle, multiply the two together, and then double that. And I don't think I left enough room for that too. So I'm going to put a 2xh right there. There we go. Does anybody want me to expand it and use FOIL or use another method? We feel good? Okay. So now I'm going to plug these two expressions, this guy right here and this one, into these two parts. We always start with f of x plus h. So I'm going to take that trinomial, the limit as h goes to 0, of x squared plus 2xh plus h squared. Then I'm going to subtract, okay, f of x, which in this case is the original problem. And it's only one term, so I don't have to worry about parentheses. I can just subtract it. And this is all over h. So what's the only difference so far? Well, true, but I'm talking about the overall problem. What's the only addition that I've had here? The limit portion. Everything else is going to be the same up until I simplify that. Okay, well, what do you notice? Okay, well, the x squareds are going to cancel. Okay. Now, 2xh over h plus h squared, okay, what would that be? 2x plus h. So if I were simply using the formula, that's the answer I would get, right? That's the gradient of the secant line. But now I want the derivative, so I'm going to go ahead and take the limit as h goes to 0. So think about it this way. Any term at this point, any h that's left, is just going to continually get smaller and smaller and smaller until he's going to disappear. So let's imagine he gets so infinitely small, he becomes insignificant. Basically, he's gone. What are we left with? And that's exactly what Sydney said. Okay. So what do we think? Is she going to be correct on 3x squared? Okay. Let's see how we get that. Any questions on this? The only difference is when you get down to this h expression, every h vanishes. That's it. So if even if it's a term with h, even if you end up with something like 3xh, if it contains an h, it's gone. Yeah. So we're getting the h out. I know I said that yesterday, but I like it. Oh, no. Now, the derivative of a numerical value is 0. If you understand the pattern, okay, how did I go from x squared to 2x? And what? Well, there was no h in the original problem. Okay. Well, let's try another one. Let's try another one of these. Okay. Okay. Now, we already said 3x, or excuse me, x cubed. We should be getting an answer of 3x squared. So let's see. First off, we already have f of x. We don't have to do anything fancy there. So f of x equals x cubed. Okay. Now, let's go ahead and say f of x plus h. But why is this one, again, different? This time we have to cube it. Okay. So I need to take x plus h cubed. So, and again, this goes back to if you were taught there's a shortcut called the binomial theorem where you can get the answer in a second. Okay. In fact, it would be x cubed plus 3x squared h plus 3x h squared plus h cubed. Is anybody familiar with the binomial theorem? Anybody ever remember hearing that? Okay. If you are, great. Like I said, I just used a shortcut to immediately get it. And if you're sitting there going, what did you just do? Let's do it the old-fashioned way. Let's take x plus h times x plus h times x plus h. Okay. Do it the old-fashioned way. Sometimes the old ways are the best. Okay. So we already know if I multiply two of these, we're going to get that trinomial we've been seeing, right? So let's start there. I'm going to multiply these two, and that's going to give me x squared plus 2xh plus h squared. And now I'm going to multiply that x plus h. How do I multiply a binomial times a trinomial?
You
Kind of just have to do it. I like that. I'm sorry. I'm not, making fun of you. I can just see like a scenario years down the road. How do I swim, Dad? You just do it. You gotta learn to swim. You gotta get in the water. But you're gonna use the distributive property. So I'm gonna start with x. I'm gonna distribute it across all these. So what's x times x squared? X cubed plus what? Plus 2x squared h plus what? Okay, plus x h squared. And if you want to change it h squared x, that doesn't matter. They're commutative. You can reverse the order. So that takes care of the x. And now we just do the exact same thing to the h. So h times x squared, h times 2xh, and then h times h squared. There you go. And let's see, we can combine my like terms. Oh, where'd that 2 come from? Sorry. Got a little ahead of myself. X cubed, 2x squared h plus hx squared. That would be 3x squared h. That one canceled. That one canceled. Xh squared plus 2xh squared plus 3xh squared plus h cubed. So see, it still gave me the same expression that I got a moment ago. Okay. All right, is everybody okay with that? Carolina, you okay? All right. Now remember, these two here, f of x and f of x plus h, I'm going to apply to this formula. Who said, oh, God? Oh, is that Eli? Are you okay? So f of x plus h minus f of x all over h. Okay. So this guy right here, the f of x plus h, I'm going to replace it with that 4-term expression. Okay. So x cubed plus 3x squared h plus 3x h squared plus h cubed. Okay. Minus, see now I'm going to subtract, but what am I going to subtract? X cubed, the original problem. And this is all over what? H. Now you'll notice there's something I haven't done yet, and really you don't have to bring it in until the last step. If you want to go, especially if this is going to be pretty large, if you want to go ahead and simplify this first and then write your limit statement in the front of it, that's perfectly fine. Okay. What do you notice here? Okay, so the x cubes are out. Now simplify h with what we have left. So that's 3x squared plus 3xh plus h squared. Now normally just using the formula, that is as far as we've gone, right? So now I'm going to take the limit as h approaches 0. So every term that can still contains an h is going to do what? It's going to vanish, yeah. And you'll notice, what are we left with? Okay. You think you know the pattern? Oh, okay.
So the 3x, that whole term disappears, all h.
Well, no, because it's a product. So we have no idea what x is. All we know is that h is getting smaller and smaller and smaller and smaller. It's getting closer and closer to 0. So what's going to happen when I multiply something by that? By a value that's getting continually smaller, the product is getting continually smaller. So it's going to approach 0. Okay. Yes, Caroline.
For that, does the x have to be coefficient f above
You nailed it.
That's what I was thinking.
That's what you're thinking? Okay. So, Sydney, have you figured out that one? 4 over x to the third? Close. You're super close.
Was it
She's super close. Now, I'm getting a little ahead of myself. Normally, I don't even show the shortcuts because people, once they know the shortcuts, they really want to go ahead and start using them. But, we're still on the difference quotient. But I'll go ahead and show you. If I had something like 1 over, what do I give you, x to the fourth? I would go ahead and treat this, mainstream it as a negative power, so that it's much easier to apply the rule. But Carolina is absolutely correct. If I were to give you something like 12x cubed, let's say this is f of x, what's the derivative? There you go. You bring the power to the front. If there's already a coefficient there, you multiply those. So that would be 36, and then you subtract 1 from the power. So see, rewriting this with a negative exponent makes it really easy to do that. So I can go ahead and pull that negative 4 to the front. We'll see there's a 1, so it's just going to look like the negative 4 takes its place. Negative 4, x to the negative 5. Remember, with the negatives, you're still losing 1. Okay, so I would say that the answer would be negative 4 over x to the 5th would be the derivative. Okay. Is everybody okay with that? Well, let me go ahead and show you, because does anybody actually know what the derivative will do for us? Does anybody understand why we're doing this? Eli?
Doesn't it allow you, like, have the gradient of a curve?
Yes, it does. That's why we call it instantaneous rate of change. Let me give you a simple example. Okay. We're getting a little off topic here, but I like it when people, this is cool. It's math is fun. Okay. So let's see here. Let's say I were to give you f of x. And I think this is one we've already done before. Using the shortcut, I won't worry about going through the difference quotient. What's the derivative? 2x, okay? Now, if we apply the difference quotient, the limit as h approaches 0, I should be able to get that. But for right now, I'm just going to go ahead and say 2x. Now, let's go back to the original function. It's a parabola, right? Okay. Well, we've talked about this several times. The problem being that if I want to know the slope there, would it be the same as right here? No, because it's not a linear function. The slope won't be constant. So that's what the derivative does. It'll find you the slope at any point of x that you want. So let's say I want to know what the slope of a tangent line at x equals 1 is. Well, if I take the derivative, if I plug the value of x that I'm looking for into that, well, what's 2 times 1? 2. That's okay. That's all right. I know the slope of that line right there is 2. Let's say I want to know what's the slope of x squared when x is 3. Basically, what's the slope of this line right here? Well, I take the what I want, plug it in there, I know that's 6. See, that's why we call it instantaneous rate of change. It will tell me exactly what the slope is at that particular location. And that's why the derivative is so important to us, because how many how many slopes are you going to have here? Yeah, I mean, it's just going to continue to go around and around. It's constantly changing. It is, isn't it? It's so awesome. Okay. So does that kind of make it a little more sense what a derivative does? Now, anybody who's probably maybe in a physics class or seen something like this before, you may already know the first derivative of a function is velocity. That gives you speed. Does anybody know what the second derivative is? Starts with an A. Acceleration. That's exactly right. Okay. Good, 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 good. All right. Okay. Okay, so now let's take a look at this problem right here. So basically what I was just showing you is what is going to happen in this problem. Okay, so let's go. We are going to use the difference quotient, but let's go ahead and see if you guys remember what we just said. What would be the derivative of 3x squared plus 4? Now I've heard 6x and I've heard 6x plus 4.
6x plus 4.
6x plus 4? YOLO?
Everybody else is putting 6, 6, 6.
BOGO. That's the only one I know. Buy one, get one. That's all I know.
There's also plus.
All right, well, let's see. So we want to use f of x plus h minus f of x all over h. Okay. So let's see here. First, we always go ahead and find f of x, which is just the original problem, 3x squared plus 4. Okay. And now I want f of x plus h. This is the one that usually takes the more algebra because you got to substitute a binomial in there. So for every x, okay, in my function, I'm just going to go ahead and replace it with x plus h. So 3x squared becomes 3 times x plus h squared plus 4. Okay. So we've got the 3 on the outside. Again, x plus h squared. What's that? X squared plus 2xh plus h squared plus 4. So we ultimately end up with 3x squared plus 6xh plus 3h squared plus 4. Is everybody okay with that? Okay, there's no like terms, so that's my first part of the numerator. Okay, so this guy right here, I'm going to plug him in for f of x plus h. So we have 3x squared plus 6xh plus 3h squared plus 4. Now I'm going to subtract f of x. So that's just the original problem. Now it's a binomial, so I am going to make sure to put it in parentheses. 3x squared plus 4. And this is all over h. Now, does anybody want me to go ahead and put the limit right now, or do you want to simplify this and then worry about the limit? Simplify, okay. Well, let's go ahead and subtract this. So I'm also going to do this so I just don't have to write the whole thing again. I'm simply going to drop the parentheses, but I'm going to remember to make that negative. Okay. What if anything cancels?
3x squared.
Let's see. 3x squareds are gone. 4s are gone. And let's see. Looks like I have 6x plus what? 3h. Now, if I were simply using the formula, the difference quotient, finding the gradient of the secant line, that would be my answer. But I want the derivative, so now I'm going to take the limit as h approaches 0. So any term with h goes away. So if f is equal to 3x squared plus 4, then the derivative, f prime, is just 6x. And I did mention it earlier, the derivative of a numerical value is simply 0. They just disappear. Okay. All right. Now, there's one more part to this problem. Now it says, find the gradient of the function at x equals 3. So here's what we really want to do. What would 3x squared plus 4 look like if I graphed it?
Maybe a parabola.
It's a parabola. Would it be skinnier or would it be fatter? Okay. Why?
Wait, no, it'd be fatter because don't you like?
Well, let me take a step back. Is that is that 3 a vertical or a horizontal transformation? It's vertical. So if I'm stretching it by 3, that's going to have the effect of making him skinnier. Okay, so we're going to expect a skinnier graph up 4. 2, 3, 4. So let's say probably something like this. Okay. So it's wanting me to go ahead and evaluate this. It says find the gradient of the function at x equals 3. So let's say 1, 2, 3. Okay. Well, what it's actually wanting me to do is the slope of the tangent line at that location. Well, I know how to do that. I'm simply going to plug the value into the derivative. So f prime of 3, that's a parentheses, equals 6 times 3, which would be 18. So the slope of that tangent line would be 18. So that'd be a pretty vertical line. But that's what, now, trust me, there is way more that we are able to do with the derivatives and their applications. But for our purposes, that's what we want. The derivative will allow me to find the slope of a tangent line anywhere on a function that we want it to be. Is it starting to make a little more sense now? Is anybody not sure where I'm getting a value from? What I'm doing? Hey.
Can you do this for like any like curved function, like hyperbolas or like?
Yeah. Now that you might have to rewrite it because it depends on the form it's in. I would probably, like for a hyperbola and ellipse, I would probably manipulate the equation so that it's in terms of x. Y is a function of x, and then go from there. Okay. But if I were to give you something like this, let's say f of x is equal to 6x cubed minus 5x squared plus 2x minus 1. Let's put our skills to the test. We could apply the difference quotient to this. Okay. For every x, I could plug in x plus h, then subtract this, but can you already get a sense of how big that problem would be? Okay, so what would you say the derivative is based on the shortcuts? 18x squared minus 10x
That's it, right?
plus 2. Because, see, this one here is 1, so the 1 times 2, I just pull that in front, give me the 2, but then I always subtract 1, so that'd be x to the 0. And then any number value, it just disappears. There you go. So if you really want to test yourself to see if you're doing really well on the difference quotient, you can apply it to this and see if you actually do end up with that trinomial at the end. Emily.
So if you end up with a different quotient, like without an x, that's fine. But if you're putting it in that form,
Oh yeah, basically if a term does not have h, it's fine. It'll basically stay as is. Okay. How close are we to being done with this one? I think we're really close. Okay, let's go ahead and try to, well, let's do B, because it's definitely going to take less time than A because of the cube. Okay, but we should definitely be able to finish this up on Monday. V of t is equal to t squared minus 2, and I want to evaluate it at t equals 3. Okay. Now, again, the fact that they're changing the variables, means nothing. You could say v of t plus h minus v of t over h. Or if you just want to switch the variables back to f and x, which you're accustomed to, it's not going to change a thing. You like what?
I like A and H better.
You like a and h better? Okay. So you want me to go ahead and say v of a?
No, I'm just laughing. Just say get your.
Oh.
I always go on.
It is. Thank goodness it is. All right. So let's see. What is v of t? T squared minus 2. Okay. V of t plus h. That would be t squared, t plus h squared minus 2. So what's t plus h squared? T squared plus just th? 2th plus h squared minus 2. Okay. And then just like we've been doing today, we plug it into the appropriate locations. So this guy right here is going to replace him. So t squared plus 2th plus h squared. And I'll even go ahead and tell you, normally what I like to do if I have a variable t, I like to personally go ahead and change it because a lot of times my t's just look like my pluses. And I don't want to, confuse myself. That's why I'm drawing the nice curvy t here. But anyways, if I go ahead and subtract the original function, is everybody okay if I just say minus t squared plus 2? I just went ahead and subtracted it as I put it in, so I don't have to worry about parentheses. And this is all over h. Okay, now what? Okay, t squareds are out, 2's are out. So that would be 2t plus h. Okay, now that's just the difference quotient. That's the gradient of the secant line. Now we take the limit. Now in this case, it's going to be limit h approaches 0. So my derivative is just 2t. And does that make sense with what we've seen today? Yeah. Okay. But now the problem's not done. Now it says, okay, find the gradient of that curve at these points. Well, I want to know what's the slope of the tangent line when t is 3. Yeah, so just plug it in. 2 times 3 is 6. And that is derivatives. They really are. They really are. I mean, their applications are really cool. Anyway, questions? Hey. Right now, my original plan was to have it on Friday, but I'm kind of thinking about possibly bumping it up to Wednesday. Just because that's a long time between now and then. But I also want to make sure that we can get the homework turned in before we have our quiz. So you have a homework assignment due Monday over the limits. I'll give you the next homework assignment on Monday, and I'm thinking we could probably have that done Wednesday. And so maybe we'll keep it on Friday, just so we don't rush it. Okay.